All of us physicists have enthusiastically guessed this second for more than a century, beginning around 1916. This occasion denotes a pivotal accomplishment, offering a brief look into one of the universe's most charming and puzzling peculiarities: dark openings. These grandiose Goliaths, known for their monstrous influence, remain unquestionably subtle. While they are enormous in terms of their gravitational impact, they are almost undetectable to us, making them even more baffling. One such dark opening, possibly gauging between 2 to 4 million times the mass of our Sun, may be the subject of this disclosure. Throughout recent decades, the examination dedicated to dark openings has transformed our comprehension, taking us from a state of absolute ignorance to one where we are beginning to get an intimate look at them. And now, things have taken an even more exciting turn, as physicist Michio Kaku has revealed that we have finally figured out how to look inside a dark opening. This discovery opens the door to a wealth of new information that could illuminate aspects of science we may have previously overlooked. Let us take a deep dive into the realm of dark openings and uncover what exists in them. While space is unfathomable and vast, the concept of dark openings raises endless questions. Before delving into the specifics of Kaku's remarkable findings, it's essential to understand the fundamental idea of dark openings. The vast majority of people have a basic understanding of what dark openings are, yet significant gaps in our knowledge remain. The theory of dark openings dates back to 1916 when Albert Einstein published his general theory of relativity. This theory predicted the existence of dark openings, though at that time, the idea was purely theoretical. It wasn't until about 50 years later, during the 1960s, that substantial evidence for their existence began to surface. Researchers studying the constellation known as Cygnus observed a surprisingly bright blue star emitting X-rays. This star, they discovered, was not stationary but rather orbiting a massive dark object. Upon further investigation, it became evident that these X-rays were being drawn into this object, leading to the coining of the term dark opening. This discovery was a significant turning point because it confirmed that dark openings were not just a figment of Einstein's imagination, they were real entities in space. It became clear that we needed to study them more thoroughly. Scientists worldwide began focusing their research on a particular dark opening in the Cygnus constellation, designated Cygnus X-1, approximately 6,000 light-years from Earth. This dark opening was many times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This was the first defining characteristic of a dark opening, the ability to trap light within its gravitational embrace. The concept of a dark opening is simultaneously fascinating and terrifying. A dark opening is a region in space where gravity is so strong that nothing, not even light, can escape it. Any object venturing too close to a dark opening is pulled in, and once it crosses a critical boundary, it is lost forever. This inherent danger underscores the importance of expanding our understanding of dark openings. After the discovery of Cygnus X-1, researchers embarked on a rigorous search for other dark openings. Estimates now suggest there may be over 100 million dark openings scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are challenging to detect, meaning we don't have an accurate count. What is clear, though, is that there could be billions of dark openings within our universe, highlighting their significance in cosmic research. The main point surrounding dark openings revolves around their gravity. Their gravitational force is so immense that anything venturing too close is compressed to an extreme degree until it becomes a singularity. Put simply, dark openings function as cosmic vacuum cleaners, pulling everything in with insatiable force. One of the most unsettling aspects of dark opening research is the phenomenon of spaghettification. If someone were to fall into a dark opening, they would be stretched into a long, thin shape due to the tidal forces acting on them. This stretching would occur gradually, and the individual would perish before reaching the final stage of this process. So, let's be clear, it's best to avoid falling into one at all costs. Although the nearest dark opening is located about 500 light-years away, questions about the potential dangers they pose to us remain. In 2021, a remarkable milestone was achieved when scientists successfully captured the first clear image of a dark opening. This particular dark opening was situated in the galaxy M87. The research team took numerous images over several nights, and by stitching these images together, they created a comprehensive photograph that revealed astonishing details. It turns out a dark opening is not just one giant void of nothingness as many might think. In reality, a dark opening consists of 3 distinct layers. 1. The event horizon. Once an object crosses this boundary, there is no turning back, it will inevitably be drawn into the dark opening. 2. The photon sphere, a region where light itself can be trapped in orbit around the dark opening. Any light entering this area becomes ensnared by the gravitational pull of the dark opening and cannot escape. 3. The singularity, where all matter falling into the dark opening is compressed into an infinitesimally small point. Here, the laws of physics as we know them completely break down, making it impossible to predict what could happen. What's even more fascinating and unsettling is that no two dark openings are exactly the same. While they all conform to this three-layer structure, the way they behave can vary dramatically from one to another. Typically, scientists rely on telescopes to observe celestial objects. However, with dark openings, this method isn't practical since they are invisible. Instead, researchers study them indirectly by observing the radiation they emit and the surrounding gas and dust. Sending probes, like Voyager, to explore a dark opening is impossible, as anything crossing the event horizon would be pulled into the singularity and destroyed. As a result, scientists must study these extraordinary objects through a two-dimensional lens, despite their inherently three-dimensional nature. One hypothesis regarding the formation of dark openings is that they are the result of collapsing stars. When a star burns through its fuel, it can no longer generate the energy needed to counteract gravity, leading to an inward collapse that can ultimately create a singularity. To further investigate the nature of dark openings, NASA scientists turned their focus to the core of the M87 galaxy. Here, astronomers observed a massive whirlpool of superheated hydrogen gas rotating at an astonishing speed of 1.2 million miles per hour. The sheer force of this rotating gas should have caused it to fly apart, yet it remained intact. Scientists theorized that a titanic mass at the galaxy's center, measuring as much as 2 to 3 billion times the mass of the Sun, was holding it in place. This mass could only be explained by the presence of a dark opening. However, dark openings may not always be formed by collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating dark opening. Kerr's solution showed that instead of collapsing into a point, a rotating dark opening would form a thin disk, a phenomenon known as the ergosphere. The ergosphere is a region surrounding the dark opening where the laws of physics begin to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, commonly known as a wormhole. This hypothetical tunnel would connect two separate regions of spacetime and, in some theories, might even link two parallel universes. If someone were to fall into a dark opening instead of being crushed, they could theoretically travel through this wormhole and emerge in a different universe, or even at a different moment in time. To understand how a wormhole works, we must first grasp the concept of spacetime. According to Einstein's theory of relativity, space and time are intertwined, forming a four-dimensional fabric. Objects with mass warp this fabric, creating a gravitational field that draws other objects toward them. Imagine spacetime as a sheet of paper. If you put 2 points on the paper and draw a line between them, that line represents the path objects take through spacetime. If you could fold the paper, you'd create a shortcut between the 2 points, much like a wormhole connecting two distant regions of spacetime. Wormholes are not merely science fiction. They are a direct prediction of general relativity. However, no one has yet observed one, and they are inherently unstable, likely collapsing almost immediately. The potential for wormholes to serve as travel pathways through spacetime has fascinated physicists for decades. While the idea of traversing vast distances in an instant, or traveling through time, is undeniably exciting, the challenges are immense. Einstein's special theory of relativity predicts that nothing can travel faster than the speed of light, which imposes a strict limit on the possibility of using wormholes for practical purposes. Additionally, even if a stable wormhole could exist, the energy required to keep it open would be astronomical, far beyond anything we can currently produce. Despite these challenges, the study of dark openings and wormholes continues to inspire scientists and push the boundaries of our understanding. As technology advances, so does our ability to unravel the mysteries of these cosmic phenomena. The exploration of dark openings offers a glimpse into the fundamental workings of the universe. They challenge our understanding of physics, test the limits of human imagination, and invite us to confront the unknown. While there is still much to learn, one thing is certain. Dark openings hold the key to some of the greatest secrets of the cosmos. Possibility of wormhole travel, essentially with our current comprehension of material science, has been a topic of interest. As of late, a specific kind of wormhole, known as the CR wormhole, after Royer, has captured the imagination of many. This theoretical wormhole would connect two distant points in spacetime, potentially even linking different universes or moments in time. Critics, however, argue that the CR wormhole might be unstable or difficult to navigate due to extreme radiation and quantum-level forces. Some physicists point out that Einstein's equations, used to describe black holes and wormholes, do not account for the quantum forces that govern subatomic particles. To truly understand these phenomena, a new theory that combines quantum mechanics with general relativity is required. Such a theory, known as a theory of everything, could explain how the universe functions at every scale, from the smallest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for decades. One promising candidate is superstring theory, which proposes that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is seen as a symphony, with different particles corresponding to different vibrations of these strings. Superstring theory also provides potential explanations for black holes, wormholes, and other exotic phenomena by demonstrating how strings warp the fabric of spacetime. Despite its promise, superstring theory remains highly speculative, as it requires additional dimensions of spacetime that we cannot yet directly observe. These extra dimensions could be so small that they are effectively invisible to us. Some theorists suggest that these dimensions were more prominent at the beginning of the universe, during the Big Bang, and collapsed as the universe expanded and cooled. Superstring theory's potential to explain black holes, wormholes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of spacetime, black holes, and the universe itself, it's clear there is much more to learn, and perhaps even more to discover, about the nature of reality. Standing on the brink of such monumental revelations, one key realization remains: we are only beginning to scratch the surface of understanding black holes and their true nature. Michio Kaku's work in the field of string theory and the ideas surrounding quantum gravity have only begun to offer potential answers. Although we have managed to gain a clearer picture of black holes through technological advances, such as the Event Horizon Telescope and new methods of indirect observation, much remains beyond our comprehension. The frontier of theoretical physics, especially regarding black holes and spacetime, remains an incredibly active area of research. While much theory and exploration lie ahead, black holes have become central to discussions about the origins of the universe itself. String theory proposes that the collisions of universes could lead to the formation of new ones, and black holes might be fundamental in this process. Such a theory could suggest that our universe was born from a collision of two previously existing universes, or perhaps it might imply that we reside within a black hole itself, an idea that would surely overturn our understanding of the universe. If this concept proves true, it could challenge everything we assume about the Big Bang and lead us to see black holes not only as destructive forces but also as potentially creative ones, acting as gateways to other realms or parallel universes. While the idea that black holes could act as portals to other universes or enable time travel is enticing, this concept remains within the realm of theoretical speculation. The mechanics behind wormholes and the ability to navigate through them remain a major mystery. Even if wormholes were stable enough to form, there's the question of whether the extreme radiation and forces near these structures would render them impassable. Some physicists speculate that if we could stabilize a wormhole, it might theoretically allow travel through time or across distant points in the universe. However, that remains a distant dream, given our current technology and understanding. When we view black holes from the perspective of quantum mechanics, we encounter even more intriguing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales, and the laws of physics seem to break down entirely when considering objects like black holes. This disparity between quantum mechanics and general relativity has been one of the most significant challenges in theoretical physics. Theories like superstring theory offer a potential framework for reconciling these differences by introducing extra dimensions and providing new insights into the nature of gravity. However, this theory has yet to be experimentally confirmed, and many of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to combine these two great pillars of physics, quantum mechanics and general relativity, into a unified theory that can explain the full spectrum of phenomena across all scales. Such a theory of everything wouldn't just provide a deeper understanding of black holes and other exotic objects in the universe but could also shed light on the very nature of spacetime itself. The concept of multiple dimensions, as predicted by string theory, may help explain the hidden forces that govern the universe. It suggests that what we perceive as a four-dimensional reality might actually be just a small slice of a much larger, more complex structure. Another area of intense study is the role black holes play in the formation of galaxies and the larger structure of the universe. The discovery that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions about their impact on galaxy formation, star formation, and even the ultimate fate of the universe. That black holes could play such a significant role in shaping the universe adds another layer of complexity to their already enigmatic nature. Additionally, the intense radiation emitted by black holes, so-called Hawking radiation, named after the famous physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of the information that falls into a black hole. For decades, scientists have debated whether information is lost forever when it crosses the event horizon of a black hole, a concept known as the information paradox. Hawking's groundbreaking work suggested that black holes could emit radiation that slowly causes them to evaporate over time, potentially resolving the paradox. However, this remains an area of active research with no definitive answers yet. What is clear is that the study of black holes has not only provided us with remarkable insights into the nature of gravity, space-time, and the universe as a whole but has also opened the door to a new frontier in physics. Black holes challenge our understanding of the laws of nature and continue to provide fertile ground for new theories and discoveries. As our observational tools improve and as we delve deeper into the quantum and relativistic realms, it is likely that we will uncover even more surprises, reshaping our view of the universe in the process. The mysteries surrounding black holes, wormholes, and the fabric of spacetime are deeply tied to the limits of our current understanding of physics. While breakthroughs in theoretical physics such as string theory and quantum gravity offer potential frameworks for exploring these enigmatic phenomena, much remains speculative until we can find empirical evidence to support these ideas. Advances in observational technology such as gravitational wave detectors like LIGO and Virgo have already revolutionized our ability to study black holes indirectly. The detection of gravitational waves, ripples in spacetime caused by cataclysmic events like black hole mergers, has provided unprecedented insights into the dynamic nature of the universe. These observations not only confirm key predictions of Einstein's theory of general relativity but also open new windows into the study of objects and events previously thought inaccessible. The Event Horizon Telescope (EHT) represents another monumental leap in our ability to visualize black holes. By capturing the first-ever image of a black hole's shadow in 2019, the EHT provided direct observational evidence of the event horizon, a boundary beyond which nothing, not even light, can escape. This achievement marked a new era in astrophysics, allowing scientists to study black holes in greater detail and test theoretical predictions about their behavior. Despite these advances, many fundamental questions remain unanswered. For instance, the information paradox, whether information that falls into a black hole is truly lost, continues to be a subject of heated debate among physicists. Resolving this paradox may require a deeper understanding of quantum gravity, a theory that unites the seemingly incompatible frameworks of general relativity and quantum mechanics. Some researchers propose that information is not lost but rather encoded on the event horizon in a holographic manner, a concept stemming from the holographic principle. This idea suggests that all the information contained within a black hole could be stored on its two-dimensional surface, challenging our traditional understanding of space and time. In addition to their role in theoretical physics, black holes may hold practical implications for the future of humanity. If wormholes or similar structures could be stabilized and navigated, they might enable faster-than-light travel or even time travel, transforming our understanding of space exploration and the nature of reality. While such possibilities remain purely speculative, they inspire ongoing research and fuel humanity's curiosity about what lies beyond the boundaries of our current knowledge. The study of black holes also intersects with broader cosmological questions, such as the ultimate fate of the universe. Theories about the end of the universe, whether it will end in a big crunch, big freeze, or big rip, are deeply influenced by our understanding of dark energy, dark matter, and the role of black holes in shaping cosmic evolution. As we continue to explore the cosmos, black holes serve as both scientific enigmas and philosophical touchstones, challenging us to question our assumptions about the universe's origins, structure, and destiny. They remind us that, despite the vast strides we have made in understanding the natural world, there is still much to learn about the fundamental forces that govern existence. The journey to uncover the secrets of black holes and spacetime is far from over. With each new discovery, we take another step toward answering some of the most profound questions in science, and perhaps, in doing so, uncover truths about ourselves and our place in the universe.